And today, we're going to dig into that secret weapon, Terzaghi's factor of safety. So here's the game plan. First, we're going to look at the simple, powerful equation that's at the heart of all this. Then, we'll break down all the terms so we're all on the same page. After that, it's time to get our hands dirty with a couple of real-world examples. First, figuring out how much a foundation can actually hold, and then we'll flip it around to see how big that foundation needs to be. Finally, we'll wrap it all up by talking about why this one concept is so critical for pretty much everything built around us. Okay, so imagine you're an engineer. You've got this incredible design for a new building, but the very first thing you have to deal with isn't the steel, it's not the glass, it's the ground. And the ground, well, it can be pretty unpredictable, right? It's got limits. So the real question is, how do you build something on it and be absolutely positive it's not going to fail? And that is the big question, isn't it? It's a super high-stakes puzzle because you just can't get this wrong. You have to know the absolute maximum limit of what the soil can take. And even more importantly, you have to know just how far back from that limit you need to stay to be completely 100% safe. Well, the answer is surprisingly simple. It's called the factor of safety. Think of it like this. Your car's speedometer might go up to, say, 150 miles an hour, but you don't actually drive that fast, do you? Of course not. You build in a safety margin. And that's exactly what this is. It's a number that lets engineers say, okay, we know the ground could hold this much, but we're only going to load it up to a fraction of that, just to be safe. It's the ultimate safety buffer. And here it is, the core principle in a super simple formula. All this says is that the allowable capacity, that's the safe pressure we can use for our design, is just the soil's ultimate capacity divided by our factor of safety. That's it. It's so simple, but unbelievably powerful. Okay, so we've got these two key ideas here, ultimate capacity and allowable capacity. Before we can start plugging in any numbers, we've really got to understand what each one means. So let's break them down real quick. This really gets to the heart of it. On one side, you've got the ultimate capacity. That's the breaking point, the absolute limit where the ground would literally fail. But engineers don't work with that number. They work with the one on the right, the allowable capacity. That's our safe zone. It's way lower because you never, ever want to get anywhere close to the breaking point. So how do we figure out that ultimate limit? Well, we use this famous equation from Terzaghi, who's basically the father of soil mechanics. Now, I know it looks a little scary, but stick with me. It's actually just adding three things together. The first part is about how sticky the soil is. It's cohesion. The second part is about the weight of all the soil around the foundation. And that third part? That's about the friction from the foundation size. That's all it is. And what about those N values in the equation? You can think of those as kind of like cheat codes for engineers. They're just standard numbers you look up in a table. They're based on something called the soil's friction angle, which is just a fancy way of saying how well the soil particles lock together. In our case, the angle is 25 degrees, and that gives us these three values right here. All right, enough theory. Theory is great, but let's see how this thing actually works in the real world. We're going to take everything we just learned and use it to solve a classic engineering problem, figuring out just how much weight a foundation can safely hold. Okay, let's put on our engineer hats. Here's the situation. We've got a square foundation, 2 meters by 2 meters. We know all the details about the soil it's sitting on, and most importantly, we've been told to use a factor of safety of 3. So the question is, how much load can we safely put on this thing? We're going to tackle this in 3 simple steps. First, we use that big Terzaghi equation to find the soil's absolute maximum strength. Second, we apply our factor of safety to bring that number down to a safe level. And third, we'll figure out the total load for our specific foundation. Easy enough, right? All right, let's do the math. We're taking all our known values, the soil stickiness, its weight, the foundation size, and our N factor cheat codes, and we just plug them right into the formula. We run the numbers, and what do we get? The ultimate capacity, QU, is about 1,078 kilonewtons per square meter. That's a huge amount of pressure, and that's the point where things would start to go very, very wrong. And now for the most important step of all. We take that scary ultimate capacity number and we divide it by our factor of safety, which is 3. That gives us our allowable capacity, Q all, of about 359.5 kilonewtons per square meter. This is the safe number. This is the one we can actually design with. Okay, last step. We know the safe pressure is about 359.5 for every square meter. Our foundation is 2 meters by 2 meters, which gives it an area of 4 square meters. So we just multiply those two numbers together, and we get our final answer.
This foundation can safely support a total load of 1,438 kilonewtons. Job done.
Okay, that was pretty cool. But what happens if we flip the problem on its head? What if you already know how much your building is going to weigh, and now you have to figure out how big the foundation needs to be? Let's give that a shot.
So for this one, we know the allowable load is 1,000 kilonewtons, and our factor of safety is still 3. The soil is the same, but this time, the thing we don't know is B, the width of our square foundation.
Now this is where it gets a little clever. See, we can express the ultimate capacity in 2 different ways. From the load side, we know the ultimate load has to be our allowable load of 1,000 times our safety factor of 3, so 3,000. And we divide that by the area, which is B squared. But we can also express it using Terzaghi's equation, just with B as an unknown. Since they both equal QU, they have to equal each other. So now we've got this equation. And if you're looking at that thinking, how do I solve that for B? You're not wrong. It's tricky. So what do engineers do? They use a smart kind of trial and error. You just assume a value for B, plug it in, and see if both sides of the equation match up. If they don't, you adjust B and try again, getting closer and closer each time. And after a few rounds of that process, we find that the value for B that makes everything work is about 1.77 meters. So, in the real world, we'd round that up to a nice clean 1.8 meters. And just like that, you figured out the size of the foundation needed to safely support that 1,000 kilonewton load. So we've been pretty deep in the numbers, but let's take a step back and look at the big picture. Why does this whole concept, this factor of safety, matter so much? What's the real principle at play here? And this right here is the golden rule. It says the factor of safety should be at least 3, not 2.9, not 2.5, a minimum of 3. But why? Because the real world is messy. The soil in one spot might be a little weaker than you thought. The load from the building might not be perfectly distributed. That factor of 3 is our buffer against all those unknowns. It's not just a suggestion, it's a promise of safety. So when you boil it all down, what have we learned? The factor of safety is that critical buffer, that gap between what the ground could take and what we ask it to take. It's how we turn complicated theory into practical, safe designs. And it's this simple idea that lets us live and work in these massive structures without a single worry.